it's input impedance, for instance. Right? We looked at the gain, but let's look at the input impedance and see what the input impedance looks like. Again, let's look at the input impedance from two different ways. You can look at the input impedance when you're applying a differential signal. Right? If I have a differential signal, I know what the equivalent half circuit is. And now, as you can see, this half circuit concept is quite powerful because it allows you to analyze this circuit without having to look at both transistors. You can just look at one, and depending on what kind of signal you're dealing with, whether it's differential or common mode, you draw the appropriate half circuit and you analyze that. So for a differential circuit, we saw that the equivalent half circuit is like this. Or even from a kind of a more convenient way, this is the equivalent half circuit. So this is VIB over 2, and this is VOD over 2, and this is RC. And you know what I mean when I draw this. When I draw it this way, what I mean is that I'm really looking at the small signal model. I'm really looking at that. But I want to avoid drawing these things as much as I can. So I want you to, in your head, think of this transistor as that. You have to practice that. We'll do this multiple times. Okay? Because then, otherwise, we'll have to redraw everything, and when we are talking about a 30 transistor circuit, then we have to draw a really huge small signal model. You don't want to be doing that. Now, okay, so we have this relationship between VID and VOD, and that's the equivalent half circuit. Now, I'm interested in the input impedance of this thing. So, what is the input impedance here? If of this half circuit, what is RA? Of this half circuit, it's called R prime. R pi, right? It's just the input impedance of a non-degenerate common emitter. Now, what can I say about the input impedance? What does this input impedance represent? It's really the ratio of the input voltage, which is VID over 2, over the input current, which is, let's say, IN. Right, let's call this IN. That's this Rn prime, or that's R pi. But what is my input impedance for a differential signal? If I had a differential input voltage connected between these two, that input impedance by definition is the ratio of VID over IN. Right? The current is the same, but the voltage is half of that. So in other words, the actual input impedance for the differential mode is going to be, which is by definition VID over IN, based on this equation is going to be 2R pi. Right? Which kind of makes sense. You get an R pi from one side and an R pi from the other side. So this gives you an R pi, this gives you another R pi. So the input impedance for the differential signal is 2R pi. Now, how about the input impedance for a common mode signal? Is it going to be the same? Going to be different? We don't know. Let's find out. So for a common mode signal, we have to look at the common mode equivalent circuit, right? So the equivalent circuit, half circuit for a common mode, we have two REEs here, and the same thing on the other side. And this was VIC and this was VOC. Now, what I'm interested in is the ratio. If I have a common mode voltage applied, what it means in this picture is that these two are shorted together and are driven by a current VIC. And what I'm interested in is the current IC that goes in, or INC. Right? So my input impedance for common mode is going to be defined as VIC over IIC, the input current mode current. Right? But if this is VIC, what is this current? Is it IIC? Remember, I have another one exactly like that on this side. So what is this current? Yes, half of IIC. So when I calculate the input impedance of this equivalent half circuit, this R prime, it is really the ratio of VIC over half IIC. And what is that input impedance? Well, that's nothing but the input impedance of a common emitter with emitter degeneration. How do I calculate that? Remember the reflection rule, right? I have stuff in the emitter, I want to move them to the base. I'm looking at it from the base side. What happens to them? They get multiplied by what? 1 plus beta. 1 plus beta. Yeah. Beta. So I get, this gives me an R pi. That gives me beta, 2 beta RE. by definition, VIC divided by IIC, and that's basically 1/2 of that, because this 1/2 goes to the other side. So it becomes R pi over 2 plus beta R2, or more accurately, beta plus 1. Okay? So is this the same? Is it smaller, larger than the differential? It's not the same, right? So this is interesting. Not only you see different gain for two different modes of signal, you see different input impedance as well. So depending on that component of the signal that's differential sees a smaller input impedance, and that component that is common mode sees a larger input impedance in general, assuming that RE is reasonably large. So even the input impedances depend on what kind of mode of operation you have. So there's common mode or differential. Now, actually, if you look at these two, you can combine the equivalent input circuit into one. You can define a kind of an equivalent input circuit for this whole thing, which looks like this. So if I say, well, I have an R pi here and an R pi there, so these are my two inputs, and then I have an REE, or I'm sorry, beta REE here to ground. That's kind of the equivalent input circuit that gives me, the equivalent network that gives me these two impedances depending on how I drive it. Right? How do we see that? If I drive this in common mode, it means that these two move up and down together, right? So they're at the same level. So they're shorted. So what do I see? These two will be in parallel, half of R pi plus beta RE. Now if I drive them completely differentially, it means that these go up and down in opposite phases, anti-symmetrically. This node does not move. Right? So it doesn't matter. Basically you just see the 2 R pi.
That should be a half beta RE.
No.
Where's that extra factor?
Because it was 2 REE to begin with.
Oh.
In the equivalent circuit, you already have 2 REE. So that 2 cancels that 1/2, yeah. Okay? So that's the equivalent. So you see, depending on what mode of operation, this circuit can behave completely differently. Completely differently. And that's a good thing about it. That's exactly what you want it to do. So let's just kind of do a quick numerical example. When you get to be that surprised, but let's just do a quick numerical example. So let's say I have a differential pair made out of bipolar transistors. Let's say I have a 5 kilo ohm. I have a pair of 5 kilo ohms as RCs. Let's say my VCC is 5 volts. And let's say I have a current source of 200 microamps. And it has an effective output resistance of large, 100 kilo ohm, not too large, reasonably large. So what is the gain of this thing? Well, what kind of gain? The first question you have to ask me, I have more than one input terminal, right? So first I say, well, the differential gain. The differential input, differential output gain. So if this is VOD, what is my differential gain? ABD, which is defined as VOD over VID, is what? Well, how do I calculate it? Well, for differential signal, I know I can look at the equivalent half circuit, right? So I know for differential signal, this node does not move. Right? This is what we call a virtual ground, by the way. That's the expression we use. It's not a real ground, but it's a virtual ground. Because for all practical purposes, it doesn't move. So you can actually treat it as a ground. So this node is a virtual ground for differential signal. And therefore, my equivalent half circuit for differential signal looks like this. So this is VID over 2. This is VOD over 2. And that's the gain of that thing. What is the gain of that thing? Minus GMRC. And what is minus GMRC? Well, let's determine GM. What is GM? GM is IC over VT. What is IC? Well, when the stage is balanced, and if these transistors are identical, if there's no differential input DC-wise, these two will carry the same current. So each one of them carries what? 100 microamps. Right? millisiemens times 5 kilo ohms. Kilo cancels milli, ohm cancels Siemens. I'm left with the gain of minus 20. Okay, so the differential gain of this thing is minus 20. From a differential input to the differential output. Now, if I just don't look at one of these outputs, if I just look at one, if I say, well, this is my output, forget about the other one, what would happen? I get half of that gain, right? Because half of it happens on one side and half of it happens on the other side. So my gain would be 1/2 of that. Now, so that's the gain of the differential gain. How about the common mode gain? Well, to determine the common mode gain, I have to draw the equivalent common mode half circuit. So the equivalent common mode half circuit has this RC again, and this would be VOC, and this is VIC, but what is this? Now I have to split this into two parts, right, in this small signal model. I can see this is RE, so I have to have twice as much on each side. So this would be 200 kilo here, and this is 5 kilo. So what is the gain of this thing? Ballpark.
Or 1/40.
1/40, right? It's the ratio of that resistor to this resistor. Because Rm is relatively small compared to that. If you want to take it into account, 200 kilo ohms plus 250 ohms. You can calculate it for 100 microns, right? But anyway, so ballpark, AB common mode is approximate, which is by definition is VOC divided by VIC. It's going to be approximately it's minus RC over R2REE, which is basically 1/40. You see the difference, right? This differential signal gets a respectable value and it's an okay gain of 2 and 20. The common mode signal, on the other hand, not only doesn't get amplified, it actually gets attenuated by a factor of 40. Which is a good thing. If you are dealing with it. Now, what is my common mode rejection ratio? The ratio of these two. So it's 20 divided by 1/40, so it's about 800. And in dBs, 800 would be what? What is 100 in dBs? 100 in dBs is, well, it's voltage, right? So dBs is 40. So that's 40, and each factor of 2 gives me a 6 dB increase, right? For voltage, right? So I have 3 factors of 2, so I have 3 6 dBs. So I have 18 dBs there, plus 40, so that's 56 dBs. And you see that even in this case, actually, although this appears like a lot, if you look at the common mode rejection of many of op-amps, actually they're in the order of 70, 80 dBs, or even higher for op-amps with higher common mode rejection. So you can see that they substantially attenuate the common mode signal while they amplify your differential signal.
And this is good for input voltages in the range of 0.1 volts.
Yes. Right, correct. But remember, an input voltage in the range of 0.1 volts corresponds to an output voltage in what range for this amplifier? 2 volts, right? So since you have a relatively good gain, of course the input signal has to be small. It doesn't mean that you can't make large signals with this on the output. The only thing is that to make those large signals without major distortion, you need to use a small input signal. Okay? Any other questions about this? Alright. Alright, so let's see if there's anything else we can do with this stage. So we did, and the input impedance we can calculate is just going to pop pi. Now, let's go back to your question actually. So let's say I want to somehow increase my input range. What do I do?
You drop RE higher and higher.
Now, if I make RE higher and higher, would this be affected? We already talked about that.
sorry,
RE
sorry.
would not help.
RE, you make RC lower.
Okay, but that would lower my overall gain of this amplifier. So I can do that.
But it doesn't make the range wider.
No, it wouldn't make my, well, it would increase my input range. Yes, true. That's one way of doing it. So you could do that. You can make RC small. common mode, basically, right? So what else can I do? Well, we talked about this, right? So we said that if you put a resistor here and a resistor there, I can increase my linear range. Now I have to make an RE, not REE, not to be confused with REE here. Let's put a 1 kilo RE here. So now what would change? Let's look at the small signal models. What would happen in the differential equivalent half circuit? Now this guy, you remember, it was this node that was virtual ground. So when I look at the half circuit, the 1K will appear here. So my new gain is going to be what? My new gain is going to be 5 kilo ohm divided by Rn, which in this case is 250 ohms, plus 1 kilo ohm. So that's 5K divided by 1.25. 4. Right? So my gain went from minus 20 to minus 4 by introducing a 1K resistor there. What? Differential gain. How about my common mode gain? Well, even in my common mode circuitry, I still have that 1K, right? Because when I split this into two equivalent 1K and 1K, it still will be hanging off of here. So I could basically, if I look at it that way, it would be 2RE and 2RE. And I break it here. So what I would have is that RE plus RE. So I have 1K here, but I already have 200 kilo ohms, so it's not a big deal. So it's already the same thing. So it makes it a little bit different, but it's pretty much the same thing. So now my gain has gone down, and what happens is that I have a larger dynamic range, but what's the price that I've paid? The gain and also the common mode rejection ratio. So now this is smaller. This is 4, so it has gone down to a factor of 5. So there's a trade-off there too. Now, what if I wanted to get more gain? Instead of less.
Increase RC.
Increase RC, okay. How do I, well, let's look at some of the DC levels. Make sure that it makes sense. So let's say, instead of 5K, I make it 50K. Let's say I want to increase my gain by a factor of 10. Let's try something here. Oh, this was 100 kilo ohm, and this was 100 microamps. So if I make this 50 kilo ohms instead of 5 kilo ohms, what happens? Well, I don't know. Let's keep the current the same. So for now, when they were 5 kilo ohm, what were the voltage drop? What were the DC voltage drop across these resistors? Oh, this was 200 microamps. So it was 100 microamps in each branch. So 100 microamps times.
There's half a volt.
There's half a volt, right? 0.5. Now, if I make that 50 kilo ohm, what is the voltage drop?
5 volts.
5 volts. So it means that this voltage is what?
0.
0. So if this common mode voltage is higher than that, let's say it's 1 volt, it wants to be 1 volt. Right? If you set it at 1 volt, can this go to 0? Before it hits 0, around the time it's kind of 0.3, this side is forward biased. So this transistor actually can go into saturation, so you have to be very careful about that. So if you make this resistor just large like that, at some point your stage will saturate. And the way to avoid that is either by having a larger VCC or keeping this voltage at a lower voltage. You're basically running out of headroom. So there's a limit to how much you can increase that resistor, except other than some practical limitations that a larger resistor also takes up more area on the chip. But so there's a limit to how much I can make this resistor larger and larger. So that works out to a certain point. So let's say I reached that limit. What can I do to increase my gain?
Increase the current. That's the same effect.
Well, not exactly. Kind of, right? It's the same effect, but it's true. It's true that it's the same effect in the sense that the total voltage drop is the same. Will become larger, right? Same as the previous change. So that's not going to help you much either. So what do we do? We have had a similar situation before. Delta. Yeah, it's a current source up there, an active load, right? So if I use a transistor, let's say if I could use a pair of PNPs this time, if I put a PNP transistor here and a PNP transistor there, and keep them biased at some constantly biased, make sure that there's a constant current, let's say 100 microamp in each burst, initially the balanced case, what happens is that now I can get a much higher gain. So if I look at my equivalent half circuit for this, it looks like that. So the equivalent half circuit looks like this. Right? For each half. Agree? And what is the gain of this thing? What is the differential gain? Well, it's the GM of this guy driving the impedance of this node. What is the total impedance on this node? Looking up, what do you see? ROP, right? RO of the PM. Looking down, what do you see? RON. So you see the parallel combination. The gain of this thing is GM N RON in parallel with ROP. Now, numerically, let's say I have a VAN of 100 volts, VAP of 50 volts. So what is that? Now, RON, which would be VAN divided by IC, is 100 volts divided by 100 microamps. Right? That's the IC. What is it?
That's one mega.
What? Yeah, micro gives you a mega. Right? So it's 1 mega ohm, and the other one is half a mega. So the parallel combination is something like 330 kilo ohm. So 330 kilo ohm times the 4 millisieverts. Kilo cancels milli. 4 times 330 is 1200. Ballpark. Right? So you get a gain of approximately AV of 1200. Much higher than 20. But of course now, let's say you want to have an output voltage range of, let's say the gain is 1,000. Okay. Now you want to have an output voltage range of 5 volts. Right? Your supply is maximum 5 volts. So what does that mean in terms of the input voltage range? 5 millivolts, right? So you see, it's very fundamental to the fact that you have higher gain that your input voltage range will become smaller and smaller. Nothing magical there. Okay, any questions about this? Okay, if there are no questions about this, then we can start talking about the MOS version of differential tech. No questions? Alright, let's talk about the CMOS version. Now you can see everything we said pretty much is applicable in terms of principle to the MOSFET version. Now the difference is that MOSFETs follow a different set of equations. So if I try to calculate the large signal transfer function like we did for the calculation that led to the hyperbolic tangent, it's normal to expect something different, right? Some kind of different behavior. So let's look at an equivalent pair of NMOS transistor placed in this arrangement. This is ISS, and we're connected to some sort of load, and this is ID1, this is ID2. Well, let's call this I1 and I2. Now, what can I say about the sum of I1 and I2? It's exactly equal to ISS because I don't have the alpha factor here. I don't have a gate for it. Right? Now, the other thing that I need to do is just say, well, if I have an input differential voltage VIV, what is so I have to basically write the KVL around it. So this one is VGS1, and this one is VGS2, right? So I know VGS1 minus VGS2 is VID. But I also know one more thing. I know the general behavior of a MOSFET. I know ID is mu n Cox over 2 W over L, and let's assume that these have the same W over L, otherwise it's going to be even symmetrical, times VGS minus VT squared. parameter, let's call it K prime, to make things simple in our calculation. We'll come back to this at the end of the calculation. So it's really K prime. So I can write VGS in terms of ID as ID over K prime square root plus VT. If I solve for VGS in terms of ID, solve that quadratic equation. Right? That's what I get. So let's plug that into here. So I get square root of ID, well, this will be ID1, or I1, I'm sorry, over K prime plus VT, VT1 plus, or minus square root of I2 over K prime minus VT2. Now, the VT is on the threshold voltage of these two transistors, right? And in general, they could be different because of body effect, right? Because they could, the source bulk potentials could be different. But is it true in this case? Are they at the same VBS or different VBSs? See, their sources are shared. They have shared source. So they both have the same VBS, although the VT is not VT0, but it's the same voltage for both of them. So irrespective of that, these two cancel. Even including the body effect, this doesn't show up. So what you're left with is 1 over square root of K prime times square root of I1 minus square root of I2. Okay? So now, what can I do with this? I want to actually write this, I want to solve for delta I at the output in terms of the ID. The same thing that I solved for in the button. So delta I is what? Delta I is I1 minus I2. Now I can write I1 and I2, which are here, in terms of delta I and ISS. Right, so I have two equations for IS1 and I1 and I2, and I can solve those. So then I1 would simply become ISS plus delta I over 2, and I2, if I look at these two equations, right, becomes ISS minus delta I over 2. All you need to arrive at this is to add the two sides or subtract the two sides of this equation. The one gives you that, and the other one gives you that. Right? Okay, so I can plug those in those terms. If I do that, I factor 2 in the denominator, and what I'm left with is square root of ISS plus delta I minus square root of ISS minus delta I. Right? So that's the ID. Still, I want to solve this for delta, I want to solve for delta I in terms of the ID. So I have to solve this equation. Kind of a funny equation to solve. So how do I solve this equation? Well, first of all, I square both sides of this equation. So let's square both sides. And let's put this on the other side. So I get 2K prime VID squared. And then on this side, I get this thing squared, which gives me ISS plus delta I, plus this guy squared, ISS minus delta I, minus 2 times the product, which is square root of this times that, which gives me ISS squared minus delta I squared. Basic algebra. Right? So now these guys cancel. Now I have a 2 here. I have a 2 here because I have 2 of these, and I have a 2 here, right? I cancel this 2 and that and that. Okay? I could rewrite this as 2 ISS and then cancel. So what I'm left with is K prime delta VID, well, I'm sorry, VID squared is ISS minus square root of ISS squared minus delta I squared. So now I move this one to this side and the other one to the other side, so then I square both sides. So I guess ISS squared minus delta I squared from this guy, which is on this side. And then I have have this minus that on that side, and then I square it, so I guess ISS squared from that term. I get K prime squared VID to the fourth from that, and then I get minus the 2 times the product, ISS K prime VID squared. Okay? Now, this ISS squared cancels that squared by ISS squared, and what I'm solving for is really this guy. So, I multiply both sides by minus sign and take square root, so I get delta I, which is 2 ISS K prime VID squared minus K prime squared VID to the fourth, square root. So you can basically factor VID out. So you get VID square root of 2 ISS K prime minus K prime VID squared. Actually, I can even factor that part out. So I'd say VID, let's factor that part out. Square root of 2 ISS K prime times square root of 1 minus K prime, this is K prime squared. So there's a K prime VID squared divided by 2 ISS. That delta I. Now, as you can see, there's a linear part and there's a nonlinear part. Okay? So it's, and if you plot this, delta I versus VID, you see a kind of a similar behavior. Talk about that in a second. Okay, but now let's look at this term a little bit more carefully. What is this term? Well, let's expand it in terms of K prime. I know it's 2 ISS square root of 2 ISS. Now K prime is mu n C ox over 2 W over L. Right? So if I were to look at it only for small perturbation around here, my transfer function looks like that. I can drop this second correction term, right? Because the VID squared term here. So it's a higher order term. Okay? So it's only that. So for small variations, it's what this is. So what is that? Well, let me rewrite it in a slightly different way. So now I can divide it by ISS 2 and then multiply by 2. So let's get at least 2. Get rid of these 2. What is 2 times mu n C ox W over L ISS over 2? What is ISS over 2, by the way? It's the drain current of each transistor, right? So it's ID. What is this quantity? GM. So for small perturbation around here, this is simply GM, VID. For small VID. You can see that the transconductance of this differential pair, from a differential perspective, is the same as a single transistor. It's GM. And therefore it shouldn't be surprising that the gain would be minus GMRD when we put a resistor there. Same thing as bipolar. But now let's go back to this large signal equation for a second and see if you can make some sense out of it. Now, one interesting thing is that if you look at these equations, look at this. Now, at some point, you will see that actually, unlike the bipolar case, the stage can be completely steered to one side. In other words, one of the transistors can be off. And one way to see that is as follows. So let's see. Let's look at the stage now in a situation where the stage is not balanced. So there's some sort of input voltage. So let's say there's some delta VID at the input. And I want to find the delta VID, the minimum delta VID, that makes one of the transistors completely off, turns one of them off. Right? In that situation, at that point in time, what is this current? If this current is ISS, let's say I make this positive and this negative. So I want to keep this, all the current going through this guy and no current going through that guy. So what would this current be? ISS, right? And this current would be 0. So if this current is ISS, what can I say about this VGS1? VGS minus VT plus square root of the current divided by K prime, right? That expression. Just solving for inverting the basic quadratic dependence of the MOSFET, right? So now, this time ID is simply ISS divided by K prime. Right? Now, what is VGS2 at that point? Just when it starts out. What is VGS2? VT, right? Because you have 0 gate overdrive, so VGS minus VT is 0, so the current is 0. So at that point is VT. Therefore, the VID at that point that causes this, or delta VID, it would be square root of ISS over K prime. This one is that. Now what is this? Now ISS is twice the ID of the balance stage. Balance. What does it call? Just balance. If you would, it stands for. Divided by K prime. So this is square root 2 times the ID balanced divided by K prime. But what is this? That's the gate overdrive, the excess voltage you have on the gate when the stage is balanced, when these two are equal. You need to maintain a certain level above VT to make sure that the current flows, right? It's called a gate overdrive, or delta VGS. So that's delta VGS balanced. So what it tells you is that the voltage that makes this current, this stage completely switch to one side, is square root of 2 times the gate overdrive when the stage is balanced. Okay. So if you want to know what kind of voltage you need to steer this stage, right? What you need to do is to determine what is the gate overdrive at that current level. So let's say you have 200 microamps at the bottom, then you look at the gate ID, and then you have to know your K prime, or mu NC ox W over L. So given W over L mu NC ox, then that corresponds to a VGS minus VT. That VGS minus VT times square root of 2 is the amount of differential voltage that makes the stage completely go to one side or the other. And you can see, unlike the bipolar case, in this case, it's actually you can turn the stage, one side of the stage completely off. If you apply additional voltages beyond that, nothing will change. Alright? Any questions about that? Now, if I were to increase my linear range of the input, what can I do here? Of course, I could always play that old trick of the resistors here, but there's something else I can play with here in the MOSFET. What can I play with? Yeah, so I have the W and L's of the transistors, right? Those are also design parameters. So if I want to extend the dynamic range, what do I need to do here? The linear range of dynamic range. Well, increase the current, that's one way, yeah. But let's say I have a fixed power budget. I can increase the current and not that power.
You could lower the W over L ratio.
Right, I need to lower my K prime. Therefore, I need to lower my W over L ratio. So I can make it smaller, use a smaller W over L. That gives me a larger dynamic range. So if I look at this transfer function, this delta I over VID, this is for decreasing W over L. Okay. Any questions about this? Now, you can actually do exactly the same thing. You can calculate the differential gain and common mode gain for this by looking at the half-circuit equivalent. So let's do that quickly. So for half-circuit equivalent for differential circuit, we know that this node is the virtual ground for differential input, right? For small signal differential input. So the half-circuit equivalent is nothing but this. And the gain of this thing is minus GMRD, or GMRD parallel to RO, if you want to take that into account. Right? Now, how about the common mode? In case of common mode, we realize that, well, if this were an ideal current source, what would the common gain be? common mode gain. It will be 0 because there's no variation. But let's assume that there's some sort of resistor RSS. That's RSS, and you have two RSS here. You have RD here, and the gain of this thing is the gain of a common, degenerate common. Okay, so basically you have RD divided by, ignoring the body effect, it's basically RD divided by RM plus 2 RSS. Or another way of writing it when GM-RD divided by 1 plus 2 GM-RSS. So the common mode rejection ratio, which is the ratio of these two, is going to be 1 plus 2 GM-RSS. Very similar to that, in the case of the bipolar transistor. Does that make sense? Alright. Now, there's one more thing that, there are a couple of interesting things that can happen in the differential pair. So in addition to that, so if you look at this the way it is right now, what we have is a stage that if you apply common mode voltage, even if your common mode rejection ratio is not infinite, right? Even if this resistor was relatively small, when you apply common mode voltage to this or with bipolar case, right? It applies to bipolar case. There would be a change in the individual common mode levels. But both of them change at the same time. So if you always only look at the differential signal at the output, you don't see this change. If you just look at the output difference, the difference between the two outputs, you don't see it. Right? So the common mode gain, there's a common mode gain for itself, and there's a differential mode per self, but there's no coupling between them. But in reality, something happens that we create the so-called common mode to differential conversion. And that's probably the most significant effect, because usually your common mode rejection itself is relatively high. So let's look at this stage. Let me ask you a question. So I have this stage, could be MOSFET, could be bipolar. And let me just put RD and RD, let's say for now. What can cause a common mode signal, so if I short circuit these two and apply VIC, to become a differential signal, to turn it into a differential signal? Can you think of something? Yeah, it's symmetrical as is, so for as long as it's symmetrical, there would be no conversion, common mode to single element. But to maintain this exactly symmetrical, you have to make these two sides identical in values. But you can never make two resistors or two transistors that are identical. You can try to make them closely matched, but they are never identical. So there's always a difference. Let's just look at our resistance, and there could be a difference in the transistors. Now, when you have something like this, let's say the resistors are different. So you apply a second voltage. This current goes up a little bit because this resistor is finite. And this current goes up by a certain amount. So there's a delta IC, there's a delta IC, which is proportional to VIC. Right? But now, this voltage goes down a little bit more in this one for the same change in the current. Make sense? Let's say I apply this thing, there will be a change in the current because there will be more current flowing into this side. This voltage goes up. Now, but for the same change in the current on both sides, there will be a larger drop on that side. So I've created a differential signal. Correct? So this is the basis of the common mode to differential conversion. And that's why matching of the two sides of the transistor is quite important. Alright. Any questions about this? If not, I think probably this is a good place to stop. Next time, when we come back, this will be next Wednesday. What we'll do, we'll go and look at more variations of differential pairs and different kinds of stages and nodes we can use for increasing the gain and changing the parameters. And keep in mind, it's extremely important for you to understand the differential pair very well. It's one of the very basic building blocks used very often. Now, before we go, I wanted to show you something. Just let me spend a couple of minutes on this. It will take that. There are people who like to treat differential pair have it, I show it bipolar version, it works for the CMOS. So this is the standard one. And you can always throw away one of the outputs and look at the other outputs, right? Fair? You can always use one of the outputs. Just don't look at the other one. So if this becomes V out, and then you can also maintain this voltage at some bias constant voltage, right? So let's say V bias. Now, if you apply a differential signal, it's the difference of these two. The differential part of it gets amplified here, and you get half of that at the output. Right? So you can actually think of this whole thing as a box, which is a single input, single output amplifier. You can always use it as that. Now, if I ask you, if I treat it like that, exactly like I've shown, what kind of a stage is it? Well, it's of course a combination of two stages, right? Let's see. What is this? Well, forget about this RC, it doesn't matter. It could be there, it doesn't matter. Or you could remove it either because you're not using it anyway, right?
Common source, common gate.
Well, common source? I mean, this is bipolar.
I'm sorry, common emitter, common.
Is this a common emitter?
It's a common color.
This is the output, right? It's a common collector, right? It's a emitter follower. Followed by what? Common base. So it's like a common collector
Yes.
plus a common base. Now, remember, a common collector has a high input impedance and a low output impedance. Right? It's a buffer. Now, a common base has a low input impedance. So to get a reasonable voltage gain, you have to drive it with a low output impedance source, which common emitter is. Common collector is. So common collector drives the common base, and it can drive it because it has a low output impedance, and it can drive a common base. And common base is what gives you gain of GMRC. Now, if you look at this, you don't get the gain of GMRC exactly, right? You get half GMRC. Why is that? Because you have a voltage divider between this Rm and this Rm. So the gain of your common emitter, common collector, this first stage, is really it's a voltage divider between Rm and Rm. Is 1/2. Therefore, you get 1/2 GMRC because another way of thinking about it is that you've thrown away half of this. Half of the gain. You haven't used the other half. Now, this is kind of a convoluted way of thinking about this. So I'd rather you don't think about it this way, unless you have to. But it's important to be aware of it. Now, if you're dealing with differential inputs or symmetrical stages, you don't want to turn it into an asymmetrical thing, obviously. But this is not a symmetrical thing because of the way that inputs and outputs are defined. And another way of analyzing it by looking at it is that. So you can see you can look at the same stage in different ways. And it should give you exactly the same result. So that's another two-stage combination you can think of. But I don't think it's a good idea in general to think about it that way, but it's important to be aware of it. All right, let's erase it. Stare at the two for too long. Okay, any questions?
Is there any homework for this coming week?
Say again?
Is there any homework for this coming week?
Yeah. Oh, actually, sure. Yes, there will be a homework.
Oh, were there any handouts?
No, well, this is actually very similar to a box, I think.
Okay.
But I actually will make the homework problem sets, and you can pick it up in the afternoon from Michelle's office.